Our learning objective for this lesson is to discuss how and why nitrogen ends up in tile drainage. We'll also learn some rule of thumb values for normal tile drainage nitrate loss. I'll start this week with recommending, this is required reading. You read pages 1 through 11 of the 10 Ways booklet. This booklet is a regional collaboration that does a good job of explaining nitrogen loss in subsurface drainage in an extension style format. You can also feel free to browse later chapters in that book, knowing that we're going to cover some of those conservation practices later in the course. First question about nitrogen loss. How much do we lose through subsurface drains? Several years ago, I did a large-scale review of every single published drainage study in North America, which ended up being about 50 years of drainage research. And I compiled that information into a database. I later had a student add to this database that allowed us to create graphs like this that answer big basic questions about what we're seeing with drainage water. So the graph in the middle of the screen is flow-weighted annual nitrate concentration, and the graph on the right is annual nitrate loss. Average tile drainage nitrogen concentrations tend to be around, the mean tends to be around 13 from our database, but you can see, of course, there's a range there. And actually, because these data were not normally distributed, the median rather than the mean is a more appropriate statistic to talk about. And even our median is nearly 12, 11.80 milligrams nitrate nitrogen per liter. I want to put this in context of something we talked about before. Our very own Illinois nutrient loss reduction strategy recommended nutrient criteria for the state of Illinois. It's not a direct apples to apples comparison because the graph I just showed you was nitrate nitrogen concentrations, and the recommended criteria I'm showing here are total nitrogen concentrations, so those are different forms of nitrogen. But nevertheless, this recommended criterion is much lower than the average rule of thumb drainage concentration we generally see here in North America, with the mean and median both definitely above 10 milligrams nitrate nitrogen per liter based on that last graph. This raises the issue in tile drained areas where a large portion of the wadable streams, which you see referred to here, a large portion of the wadable streams will be composed of tile drainage water. It's going to be very challenging to meet these criteria as laid out here, unless we really get serious about conservation practices. Coming back to the graph, the annual in-loss in kilograms of nitrogen per hectare, mean was 27.2, median was 21.1. Given what we know about typical nitrogen application rates, rule of thumb application rate around 180 pounds of nitrogen applied per acre. That translates into around 200 kilograms of nitrogen applied per hectare. That means that in terms of nitrogen balance, losing 20 to 30 kilograms of nitrogen per hectare is not insignificant when you think about these as flows in your nitrogen balance. Nitrogen loss is not insignificant. Nitrogen losses in subsurface drainage can range greatly based on many factors. The nitrogen cycle is complex because it exists in many forms naturally in the environment. Nitrogen exists in many forms naturally, and nitrogen easily changes between different forms. However, one simplifying factor is that we're nearly always talking about nitrate nitrogen when we talk about nitrogen in subsurface drainage water. So let's talk about why nitrate specifically leaches, whereas other forms don't. I'm going to talk about mineralization, nitrification, and soil cation exchange capacity. We've talked about the nitrogen cycle before, and this is an illustration that you'll see in your reading. I want to highlight here mineralization and nitrification as a part of the nitrogen cycle. Mineralization is the conversion of organic nitrogen to the form of ammonium, and nitrification is the conversion of ammonium into the nitrate form. So those two processes matter in our soil, along with cation exchange capacity. If you've had a soil science class, you'll know that the soil's cation exchange capacity, CEC, refers to the soil's ability to hold on to cations. Cations are those positively charged ions in the soil. Is nitrate a cation or an anion? Nitrate is an anion. It has a negative sign, NO3 minus. And so because the soil has a cation exchange capacity, and as we convert forms of nitrogen through these processes into nitrate is an anion, and so it's just simply not held by the soil like a cation would be. I'll also write out for you on the screen other forms of nitrogen just for your reference. Nitrite with an I and ammonium are typically not present in our drainage water. We typically don't even analyze for nitrite or ammonium separately because they're just present at such low amounts. Side note, drainage water, subsurface drainage water in Ireland actually does contain a lot of ammonium and not much nitrate. So there's a little bit of a global aspect there, just a little bit of a global difference. And then we referred to the term total nitrogen with our Illinois nutrient criteria. Total nitrogen is the summation of all forms of nitrogen present in a water sample. There's a variety of factors which each vary with time and with space that impact nitrogen loss through subsurface drains. There are both controllable factors and uncontrollable factors that impact how much nitrogen we send downstream. I'm going to start with the uncontrollable factors because these are the hard ones to do. Arguably the most important driver of nitrogen loss through tile drainage is how much rain we get. Simply put, you get a lot of rain, you're going to have a lot of drainage, and you're going to have a lot of in-loss. That's just simple kind of fact of this lesson. More rain equals more drainage equals more in-loss. Rule of thumb, roughly a quarter of your annual precipitation volume, 20 to 30%, will leave your field through your tile drain. But it's actually about 4 months of the year that are the most important for when drain pipes are flowing and for when we're sending a lot of nitrogen downstream. So you see this modeled data from the University of Minnesota. March, April, May, and June were the months where they had a lot of drainage, where they modeled having a lot of drainage over this 85-year simulation. Those are just the months where the drainage is a relatively bigger part of the water balance for flows leaving the field when you look at runoff, evapotranspiration, and subsurface drainage. And then this illustration also from your reading shows this trend of having the most drainage occur in spring and early summer. And this just clearly has to do with the water balance. You have a lot of rain during those months, not a lot of evapotranspiration because your plants aren't really growing yet, and so the water leaves the field as drainage. Mineralization is the other biggie uncontrollable factor impacting nitrogen loss through tile drains. The process of mineralization is driven in part by soil moisture and soil temperature, which are simply out of our control for the most part. Even when we don't apply nitrogen fertilizer, nitrate is still lost through tile drains, and that's because of mineralization. This means that nitrogen lost through tile drains is not solely, and I'm talking so slow here to make a real critical point, nitrogen lost through tile drains is not solely a nitrogen fertilizer problem. Managing nitrogen fertilizer responsibly is certainly part of minimizing in-loss through tile drains. We'll talk about that in a minute. But again, I'll reiterate, nitrogen loss through subsurface drains is not solely a fertilizer problem because of mineralization. Let me show you some of our own data to illustrate this point. We have a great research farm here in Illinois that's administered by our College of ACES, Agriculture, Consumer, and Environmental Sciences. At this farm, we have 16 individually drained plots that are each 2 acres. That means whatever we do on top of the field in terms of nitrogen management or the crop that we're growing is reflected exactly underneath the ground in the drainage water that we collect from that plot. The plots are individually drained, so there's no crossover between treatments or plots in the drainage water. We have 16 plots, which allows us to do 4 treatments and replicate each treatment 4 times. You can see our treatments here, but I really want you to just zone in on knowing we have a control treatment, control at the site where we're not applying any nitrogen fertilizer. We're growing corn and we're not applying any nitrogen fertilizer. And here is our results. The y-axis shows drainage nitrate load. This is US customary units, pounds of N per acre. And you can see all the treatments, but I really just want you to focus in on this 0 nitrogen control. We had 4 plots where we did not apply any nitrogen fertilizer and measured what came out through the tile drain. Is this bar 0? That is not a trick question. The bar is certainly not zero. We lost almost 20 pounds of nitrogen per acre, even though we didn't apply any nitrogen fertilizer. That nitrogen came from mineralization. That nitrogen got down to the tile drains because it was mineralized naturally in the soil and then leached as nitrate. Answer to the question at the top, no, not entirely. And just to drive this point home, you'll remember I mentioned we reviewed and compiled data from more than 50 years of published drainage studies. When we looked at studies where corn was grown and they had applied either zero or very low nitrogen application rates, the concentration of N in the drainage water was still not zero. So just to drive this point home, these are concentrations rather than loads that we saw on the last graph, but over 50 years of drainage research, this signal is very clear. It illustrates the same point. Taking fertilizer out of the equation does not solve the water quality challenge. Like I said before, there are both controllable and uncontrollable factors impacting in-loss through subsurface drains. For controllable factors, we'll start with cropping system. Cropping system is one of the clearest controllable factors due to how crops affect hydrology and water balance. Again, here's some data from the managed database that we created, this database that I was telling you about. There's a clear signal that annual crops versus perennial crops have greater in-losses. You'll see this both in dry years. Here are the annual crops, and then here are the perennial crops. And in wet years, same trend, even more apparent, annual crops versus perennial crops. And this is because perennials will be growing more readily in those early spring, early summer months when an annual crop either wouldn't have been planted or will still be too small to be significantly affecting the water balance. Those perennials are growing, taking up water, and changing the water balance away from drainage. Another note, which many folks find surprising, is that the corn phase of a corn-soybean rotation versus the soybean phase of a corn-soybean rotation really lose about the same amount of nitrogen through the tile drains. And that's, again, a clear and consistent trend across the literature in wet years and in dry years, corn phase, soybean phase. I promised we would talk a little bit about in-fertilizer management, and the big two components when we're talking about in-loss through tile drains for this factor are rate and timing. In-application rate is the most important nutrient management decision impacting in-loss in tile drains. This is just a management factor that provides a clear signal. Like I said, fertilizer management on its own won't solve our problem of nitrogen loss, but we do know that as nitrogen application rates increase, especially beyond the university recommended maximum return to nitrogen application rate, we do see increased nitrate concentrations in drainage. In terms of application timing of nitrogen, theoretically, the closer you apply nitrogen to when the plant needs to uptake the nitrogen, the less time that nitrogen will have to be lost to the subsurface drains. This means that the recommended timings for nitrogen fertilizer tend to be in the spring, at or around planting, or even later during the growing season, like as a side dress application. Now, data on the timing of in-application and its impact on in-loss isn't quite as clear as you would think because mineralization is happening, and you can never really forecast exactly what form of in will be available at what time for either plant uptake or to be lost to the tile drains. It's just really hard to forecast that when you're thinking about timing of nitrogen applications. But in general, these are the recommendations for nitrogen fertilizer management to minimize in-loss. Next controllable factor is drainage design. If the drainage system is designed to send less water downstream, you'll also send less nitrogen downstream. This tends to mean one of two things: using wider drain spacing for your laterals, spacing them wider apart, or placing the drain pipes closer to the soil surface. That's called shallow drainage. The trick with this approach of changing drainage design is that you need to balance good drainage for crop growth with reduced drainage discharge to minimize in-loss to the environment. So think about the golden rule of drainage here. Drain what is necessary for good crop growth and trafficability, and not one drop more. And finally, I wanted to talk about tillage because it's a common field operation that we control, but honestly, the impact of the type of tillage on in-loss through tile drains is kind of mixed. In general, for us, drain discharge or drainage volume, the amount of water we send downstream, is greater for a reduced tillage system like no-till or conservation tillage, whereas nitrate concentrations in drainage are generally greater for conventional tillage systems. So there's a trade-off, meaning that at the end of the day, the loads between all kinds of tillage systems, the nitrogen loads that you send downstream, aren't actually very different between types of tillage. With that, see you next time.